Hello and welcome to the Introduction to Thermodynamics video recording. I planned on making this a Class Connect session or recording it in Class Connect, but I thought that the video format would be easier for students to view, and also if I make any mistakes I can edit them out of the video, so go me. So this is your assignment for February 6th. This is for Miss Carden and Miss Smitty's class, and this is Miss Carden. So our warm-up question is, when we have wood that is burning, where does all that energy come from? So I'm not talking about lighting the wood, so obviously you have to have an input of energy to get the wood to start burning, but after the wood starts burning, it produces a lot more heat, a lot more energy. And where does that energy come from? So ponder that for a moment. It actually comes from within the chemical bonds of the wood. So you have carbons being held together with other carbons, and as those bonds are broken, they actually release energy. So there's wood and it has carbon in it. It's combining with oxygen, and as a result it forms ashes, and then some of that carbon becomes carbon dioxide. It combines with the oxygen to form carbon dioxide and water vapor. This is just a review of the law of conservation of mass, and we'll be learning about the law of conservation of energy in this unit. It just says that the mass of the wood and the oxygen are equal to the mass of the ash, the carbon dioxide, and the water. So just as a review of what this slide says, basically you have energy that are held within chemical bonds, and when those bonds are broken, energy is released. Another thing that you can learn from this reaction is you have energy that's being released into the atmosphere. That's because the energy that's within the products, or excuse me, the reactants in this reaction have more energy than the products. So there's more energy within the chemical bonds of the wood and the oxygen than there are in the carbon dioxide, the water vapor, and the ash that's formed. And you know that because there's so much heat that's being released into the atmosphere in that chemical reaction. Our Georgia Performance Standard for this lesson will be SC6. Students will understand the effects motion of atoms and molecules have in chemical and physical processes. And the essential question, the question you should be able to answer after the end of this lesson, is how does heat flow in chemical and physical processes? So just as an introduction to thermodynamics, we have to know what thermodynamics actually is, and it's the branch of chemistry, or science in general, that deals with energy transfer, usually in the form of heat. And for our purposes, we're going to refer to heat as enthalpy. That's one of the later lessons in this unit. We're going to learn more about enthalpy and the symbol for enthalpy and heat transfer. But for our purposes, when you hear the word enthalpy, it will be interchangeable with the word heat, though they're not exactly the same. And one thing to know in this unit is that heat can flow from one object to another, or from an object to its surroundings. And here is an example of heat flow. You have something that's hotter, and that heat is actually going to be transferred to something that's colder, and never the other way around. More specifically, what we're going to learn in this introduction is how heat always flows from warmer to cooler objects. We're going to be able to describe the motion of molecules in heat flow. We're going to be able to compare and contrast thermal energy, heat, and temperature, and then define a calorie, which is abbreviated CAL, and a joule. So there's a difference between thermal energy, heat, and temperature. And what is it? So we need to define these three terms. And I'm going to write here on this PowerPoint screen for the first time. So let's write with this pen. Thermal energy measures This might take a while. The combined motion of all particles within a substance. Combined motion of all, this is a keyword, all particles in a substance. And I'm going to explain what this means later on. I have an example, but I'm going to go ahead and define the other two terms. Heat is the transfer of thermal energy. Heat is the, I guess I don't have to put heat again there, it's the transfer of thermal energy. And temperature can be used to measure heat transfer. Let's see. And it's actually just the average kinetic energy of the particles in a substance. So the average kinetic energy of particles in a substance. So let's talk about the difference, what these definitions actually mean and the difference between these three terms. Let's go on to the next slide. So basically, this is an example I used from Bill Nye the Science Guy's video. If you look in one of your LMS lessons, I have his video embedded. But he explains that if you have a giant ice sculpture or a swan ice sculpture and you have a match, the match will actually be hotter. It will have a higher temperature, right? But the swan actually has more thermal energy. More thermal energy. And that's because there are more particles. Every substance that's not at absolute zero, which won't be anything that you ever have to deal with, I actually don't think that scientists have managed to get anything to be the temperature of absolute zero. So everything has thermal energy within it because the particles within a substance are moving. And the faster the particles are moving, the hotter they are. Okay, but you would run out of this match before you were able to melt all of the swan. So that's just an indication that there is more thermal energy in the swan because there are a lot more particles in the swan than there are in that match. Even though the match is hotter, the swan has more thermal energy because there are more particles in the swan. And this is just another example of exactly what I just said. So here you have more, I guess this is going to be water. It looks like H2O particles. You have more molecules and they have more thermal energy, even though this one is at a higher temperature, but there will be a heat transfer. The heat will transfer from the hotter solution to the cooler solution, even though this solution at 95 degrees Celsius has more thermal energy. Because this one is at a higher temperature, heat will transfer from the hotter solution to the cooler solution. So thermal energy actually takes into account the number of particles a substance has, as well as the temperature of the substance. So we're going to look at a heat transfer experiment and try to understand what happens. So the first thing that we're going to do is take a look at just the regular view, not the particle view, and watch the thermometer change. So we see on the left-hand side we have a container that's hotter, the thermometer is higher, right? And we're going to take the container and place it next to the cooler container, and you see that as those are coming in contact with each other, heat actually, or the temperature goes down on the hotter substance because heat is transferring from the hotter container to the cooler container until they have the same temperature. Now once they have the same temperature, no more heat transfer takes place. Now I'm going to heat the particles back up and look at the particle view. So I want you to watch the motion of the molecules. Notice that these molecules are moving a lot more quickly than these over here. That's because these are cooler. But when I put the hotter container next to the cooler container, notice that these particles are slowing down as they transfer heat to the cooler container, and the particles that were in the cooler container actually sped up until they have the same temperature. If you can kind of see the thermometer there in the background, they have the same temperature now, and the particles are moving the same speed now. And the question was, what happens? Well, heat is transferring from the hotter container to the cooler container. And why doesn't it work the other way around? Well, because heat moves from a hotter object to a colder object. So this is just reiterating what I just said. Heat will always flow from a hotter to a colder object. There will be no heat exchange if the objects are the same temperature. And that will be something you need to know for your test. So I wanted to differentiate between the units used to measure heat and temperature. So even though heat can be measured by temperature, there are actually different units used to express heat. So let's look at the scenario. This is going to be a big pot, and we could fill it with water. Okay, so we're going to fill it all the way to the top with water. And then we're going to put some water in this too and fill it up to the top. This one has a lot more water in it, right? This one has more water. So when we heat these up, which one takes longer to boil? I don't know if you've ever watched a big pot boil and then a small pot boil, but I know that when I make my tea, I actually, if I'm in a hurry, I'll put less water in the pot so that it'll boil quicker. I'll put just enough water in the pot in order to make my cup of tea because it will actually take less time. It takes less time. Takes less time to boil less water. Well, why is this? When they boil, they're both boiling at 100 degrees Celsius, right? So when water boils, this is boiling at 100 degrees Celsius and this is boiling at 100 degrees Celsius. It has something to do with heat capacity, which we'll talk about in one of the later lessons. But even though both of these are boiling at the same temperature, there's more water. So we have to take into account the number of particles as well. And that's where the units to measure heat come in. They don't just take into account the temperature, it also takes into account the number of particles. And the units used to measure heat are actually calories and joules are common units used to measure heat. And these are a little bit different from temperature. A calorie is actually the amount of water it takes to raise 1 gram of water 1 degree Celsius. So the amounts of water it takes to raise 1 gram of water by 1 degree Celsius. So when we are using units for heat and not just temperature, we are taking into account the amount of a substance and the temperature of a substance. Joule, basically joules are just used for physics. It's not anything that we're going to be using in chemistry in our class, but I'm going to go ahead and put the definition of joule up on the board just in case you're interested, but you will not be tested on this. For our purposes, you can just know the conversion between a calorie and a joule, and 1 calorie is equal to 4.186 joules. But a joule is actually the energy expended in applying a force of 1 Newton through a distance of 1 meter. The energy expended in applying a force of 1 Newton through a distance of 1 meter. So you can just think of this. You are pushing a box the length of a meter stick. I know we don't really deal with meters much here in the US, but the length of 1 meter and the box weighs 1 Newton. And that would be equivalent to 1 joule, the amount of energy you're expending to do that. Food calories are a little bit different from the calories that we just talked about. So we said a calorie was the amount of water it takes to raise 1 gram of water by 1 degree Celsius. Well, actually, calories on our nutritional facts on the back of packages that we eat are actually kilocalories. They're actually kilocalories. Kilocalories. And what's here on the package is actually 1,000 times larger than a regular calorie that we refer to in chemistry. A very, very subtle difference between the two is that this kind of calorie, the 1,000 times larger calorie, is actually abbreviated with a capital C. And if you're talking about only raising the water temperature of 1 gram by 1 degree Celsius, it has a lowercase c. And let's see. So the definition for a kilocalorie, or the calorie on the back of our nutritional facts, would be the energy needed to increase the temperature of 1 kilogram of water by 1 degree Celsius. And then this is just showing you that, I guess if we had a little c here, there would actually be 140,000 regular calories in 2 slices of bread. Okay, so that's just a basic introduction to thermodynamics. Next week or next lesson, we're going to be talking about the law of conservation of energy, which is actually the first law of thermodynamics, which says that energy can't be created or destroyed, it could only change forms. We're also going to be looking at some diagrams that show us that you have to input energy, usually in the form of heat, to go from a solid to a liquid or from a liquid to a gas. And then a substance, usually when I talk about a substance, I'm just talking about water because it's the easiest thing to think about, will actually lose energy to go from a liquid to a solid or from a gas to a liquid. And I will make one note here just in case I forget in later lessons that you might see something written like this on the test. So if you have a little lowercase l there, that means that this is water in the liquid form. And if you have a lowercase s, it means it's going to water in the solid form. So liquid going to a solid, you actually have to lose energy. This would be ice, right? So that makes sense because ice is colder than liquid water. So you're losing energy. And we'll talk more about that in other lessons. But for right now, what you need to do now that you've watched this recording is make sure you take the Introduction to Thermodynamics quiz after watching this. Thanks so much, and I'll talk to you guys later.